This week we're going to talk about what's called mass wasting. So that's just a general term to describe kind of a downhill movement of material. So a lot of times you probably heard it as referred to as landslides or something like that, which is I guess more of a layman's term. But so mass wasting is what we're going to use to describe all forms of landslides. Whether the material is big, huge rocks like in the picture here, or small material, fast, slow. Kind of covers everything. So when you hear that term, that's what we're talking about. So the one thing to remember is that mass wasting is controlled by gravity. It is the controlling force, which means that gravity is always acting on these materials and pulling them down. So there's this force that wants this material to move down slope. So usually the steeper the slope, the more kind of ability that material has to move down from the high to the low. So obviously, if you're living in the flat plains of Kansas somewhere and there's nowhere for anything to go, then your possibility of a mass wasting event is pretty much none. So we need some topography to have these events. So when we get to this in this little lecture, when we talk about hazards and risks, obviously this difference in elevation is one of the things that we would look at to say, hey, are you in an area that is prone to mass wasting events? And if you're not in an area where there's a lot of elevation change, then we would say no. And of course, if there is, then the chances of having these mass wasting events is a lot higher. Now, because I don't want to get confused that gravity is the controlling force. Now, there are factors that can determine whether a mass wasting event will occur. Gravity is the constant, but these other factors are variable, so it depends on, like we talked about, elevation. That's a factor, right? So we're going to run through a few of those really quickly. So one of the big factors is water. And so water can be in the material for a variety of reasons, but what the water does is it actually does two things. Now, we have to remember that the material that can move can be rock. So it could be of all the rocks we've talked about, right? It could be granites, it could be gneiss, it could be a sandstone, it could be a limestone. But it also can be sediment, just loose material. So it can be soils of some kind, a bunch of sand deposits, things like that. And so when we have the loose material, we have the ability of the water to penetrate into those materials. So we kind of know that when it rains out, the water sinks into the ground. And sometimes it's sinking into rock, if the rock has the ability to hold some water, or it's sinking into the sediment. So what that initially does is it adds some weight. So the added mass, the material, kind of increases the force that the material could move down slope. But it also actually reduces some internal friction. So we want to talk about that if we have some loose sediment and we put water in between those pieces, without the water, the pieces are touching each other and there's some resistance there based on friction. But if we throw some water in there, and the more water I can move in there, I can reduce that internal friction, which could allow it to move a little easier than if it was dry. So having lots of water is a big problem for mass wasting. So a lot of times after big rain events, we get mass wasting, and these are the reasons why: this added weight and the reduction in internal resistance. Over steepened slopes is another factor that controls, that it's determining whether there will be a mass wasting event, right? So if I have a really steep hill, gravity is pulling that down and there's a potential for a mass wasting event. If I go into that slope and decide I want to modify it because I want to change the slope because I'm going to put a building there, I might slice it down and make it steeper than it was naturally. And by doing that, I have increased the risk of a mass wasting event. So obviously, if I make it steeper, I'm making it more unstable, right? And so, of course, material will have this angle of repose, it's called. If we take loose sediment and pile it up, depending on the material, it can have a different steepness. And if I come in and modify that, then I can cause that material to increase its angle of repose. I mean, it would fail because I went in there and modified the slope and made it too steep. Other things that can control whether there'll be a mass wasting event is removing vegetation. So we like vegetation. It is a useful thing that holds material together, gives it some stability. So a lot of times as a method to stabilize slopes, we'll plant vegetation because it holds loose soils together with the roots as they penetrate into the ground, right? They're holding some of that material together. And it also protects against erosion. So when there is some rainfall and it moves down slope, remember these plants would absorb some of that water. So less water getting into the material, so we don't have that reduction of internal resistance story and all that kind of good stuff. So we definitely like vegetation. If we remove it, that's a potential for a mass wasting event. Some other factors, of course, we have to talk about geology because it's geology. So the geology could just generally mean the rock type. So certain rocks are stronger than others, or it could be the material if it's loose, right? So loose material would have the ability to move probably easier, right? And the solid rock, not so much. But if the rock is very fractured or it's weak, we could have potential movement from that. So geology is important. And then, of course, not just the rock itself, but the angle of the bed. So, we've talked about beddings and strike and dips and how things are oriented. In this little picture here, you can see that in some cases we have tilted slopes. And of course, if they're parallel to the slope angle, we can get sliding along these planes. So in this diagram here, of course, the rocks on the right-hand side are more prone to sliding along the contact between the two bedding planes. Of course, over here, material sliding down into the valley is not as problematic because the dip of the beds is not parallel to the slope, right? So in this example, this is an example of a failure that did occur where they had dipping beds falling into the valley here. And so one of the factors that caused this to fail was the fact that the beds were tilted down slope like that. So that's another factor. Amount of regolith. What the heck is regolith? It's just a generic term that describes the loose soil and materials that sit on top of bedrock. So we can maybe relate that to the story of if we were back east, let's say. We know that because of the climate there, the water causes faster erosion rates, and so we get thicker soils. And so it goes back to this loose material is easier to move than the hard material. So out here in Arizona, where we don't have thick soils or lots of material, we don't have a thick regolith. So if it rains, the potential for a movement event isn't as high as, let's say, back east, where if there could be a couple feet of loose material sitting on top of hard bedrock, and that material is easier to move than, say, the hard bedrock. So out here, we don't have that problem. So how much thick cover you have is a factor that can determine whether you would have an event or not. And then, let's see, finally, weight. So we talked about weight a little bit, and that was the idea of water adding weight. But of course, we can add material to slopes. So if we want to put a building up there, structures, things like that. So of course, a lot of times in California or Oregon, near the coast, it's beautiful. We want to build a lovely home at the top of the hill. Unfortunately, that adds weight and mass to the slope, and then that can initiate a mass wasting event. So these are the things we would want to evaluate if we were looking at slopes. If you're ever going to buy a house and determine, hey, that's a great place to live, I'd like to live on that really steep slope, you want to investigate some of these properties. What's the geology look like? How much weight are you going to add to it? Right? What's the steepness of the slope? How much water penetration are you going to get? All these kind of things are things we want to take a look at when we're evaluating whether a slope is stable or not. So there is an attempt, like everything else in geology, to group or label things like we did with faults. We said, hey, these are dip slip faults and these are strike slip faults and things like that. So in this class, we're not going to get too picky, but in general, there's really, even though there can be three, there's really kind of two things we focus on. And so it's type of material and the type of motion can give us the ability to name some of these events. And so for us, we're just going to differentiate between whether it's the loose stuff, so the sediment, so regolith soil, or it's rock, bedrock, right? So the three rock types we talked about. And so, of course, there's things in between. And like every science, if we wanted to be experts in mass wasting, we would have, probably 50 names for these events. But in this class, we're going to stick to kind of the basics. And then we have the type of motion besides the material. So here's a couple ways that things can move. So they can fall. Of course, that's a kind of a free fall. So if you have a very steep cliff and rocks fall kind of straight down or pretty straight down and impact the ground, right, that would be a fall event. We have sliding events. We know where we see, like in that little diagram I showed you of the dipping beds. If we can identify a surface, sometimes we have material sliding along a bedding plane. And so we can identify that. That would be a slide event. And when we add some water, we can get these flow events. And so you probably heard more of these events than anything else, because California, unfortunately, gets lots of rain, and then the soil gets wet, and we get mud flows. And so that would kind of be our naming convention. We're going to call it mud, because that was mainly the material that moved. And how did it move? Well, it flowed because it was pretty fluid, because there's a lot of water associated with that event. So we can name it doing those things. So we can have rock falls, we can have rock slides, we can have mud flows, we can have debris flows. So we kind of look at those things and try to name them based on what moved. And for us, it's just going to be, like I said, the loose stuff or the hard bedrock. And then how did it move, if we can identify that. And of course, there's some other names, of course, that don't fall into the convention, like this last one called a rock avalanche. In extreme events where material falls from very high elevations, as it lands and it breaks apart, it actually kind of gets some air trapped beneath it, which reduces the friction between the debris and the bedrock that it's moving on, and it can allow these big, huge rock avalanches to travel super fast, super far. They're kind of rare. Like I said, you need these kind of really high elevation falls for that to happen. But when we can identify those, and sometimes we do that by, what is it? It's mostly rock. But how did it travel so far? Usually we need fluids to allow material to travel far distances. So to evaluate a rock avalanche, we might see, of course, the rock debris. But if it has traveled from its source maybe miles, we would maybe make that connection that this was a rock avalanche. What else I got for you? Oh, and then, of course, we have things that move super, super slow. And the name for that is just called the creep. So you probably wouldn't even notice some of these things. These are maybe the elevation or the steepness of the slope isn't very steep, but there's enough soil there that it slowly creeps over, years. And we can identify those, of course, based on these kind of deformations at the surface, fences, and maybe the soil cracks or things like that, but they're not going to be catastrophic. All right, so here's a bunch of names, right? So we talked about some of these. We can do the rock fall, rock slide, mud and debris flows, earth flows. Slump is a kind of an unusual one we'll talk about, and the creep is the very slow-moving one. So I know you kind of get the idea, but we'll just show you some little images and diagrams for a couple of these events. So we would identify this as a rock fall because the material that's moving is the rock, and it's mostly just falling down slope. Let's see, and some images. So a lot of times these events that are more catastrophic will leave big scars where they take out the vegetation. And so even from a distance, you can identify a rock fall or even a rock slide or a mud flow because you can see the change in color on the mountain slopes, mostly due to the removal of the vegetation as the material moves down slope. And they can obviously be very large. We can have very large rocks or small, it doesn't matter. The sliding event we talked about was usually, if it's a rock slide, it's bedrock, and it's the dipping bedding planes that we're worried about. And so we can identify those as failure planes and see that the material slid down a defined slope. And they can have these, mostly we argue it's bedding planes. That's what we see more commonly. But if we have, I know the term foliation makes your head hurt because you have to think back to metamorphic rocks, but we know that when rocks get foliated, they have some linear features, and those can be weaknesses also. Or even the exfoliation we talked about, when things uplift and fracture and crack, they can move along sliding or fracture planes and things like that. Oh gosh, what else? More, you say? This is just related to that event I was telling you about where there was heavy rains that fell on the slope, and this big rock slide kind of moved down into the valley and caused some issues. A rock avalanche, that's the story of these materials that travel really, really far, and it doesn't seem possible because there wasn't any fluids involved or very little. But it's this idea that, and this is an example of one, there used to be a town here that far in the distance there was a material that fell from an extremely high elevation, it hit the ground and broke into all these pieces, and it trapped some air under that and it allowed it to move down the valley super fast. And of course it came out into the opening here and dumped all the material and did some damage there. Mud debris flows. So we see a lot of these probably in the news we think about with California. After rain, heavy rains on some of the slopes there, they get movement of material. So what's the difference between a debris flow and a mud flow? Well, we would look at the material that's being transported. If it's mostly fine material, small pieces, we would call it mud. If it's got trees in it and it's got, you know, big rocks and boulders mixed in, so we might define it as a mud flow, things like that. We know we talked about our lahars. We talked about volcanoes as a hazard with that, which is just a mud flow really, but it is specific to a volcano because it involves volcanic materials. The slump is kind of this unique one, and once again, if you were a geologist going out in the field, you would identify it as slump because you would see some of these features. Usually it's the fact that it has this arcing feature and these little scarps. Almost looks like a fault. If you were running around out here, you'd be like, oh, this could be a fault plane. Maybe there's some movement along a fault here. But instead, you're having this failure in this arcing fashion. And then you have this material move up here, and it causes usually multiple scarps like that. It's usually it's not really bedrock, it would be soils or things like that, so some loose sediment that can move like that. Doesn't move super fast, but it can, you know, move in jerks and starts like that. So some images to, we got a little carried away there. You could see these are the scarps here. So once again, maybe if you're just hiking along, you're like, holy crap, what happened here? You think maybe there's a fault because it looks like this block moved down. But if you investigated the whole area, you would see that there is this feature here that's really located here, and it's not this defining fault plane over, you know, miles. And you'd see this downdrop material that's blocked here, and you could see the multiple scarps here and some flow in the loose sediment. So that, or here's another image of that, a little more weathered one here. And earth flow, you know, for our class, we might call it still like a mud flow, but when we think of mud flows, we think more fluid. Here it's less fluid, but really thick soils here. So really humid areas where we have lots of thick soils and not a lot of bedrock, we can get earth flows like that. And just some images of that. You can look through those. We talked about creep. This is the super slow deformation of a hill slope. And like I said, a lot of times you're only noticing it because you see some weird features like a fence being bent or things like that. If you could see a side view like this, you could see that there's some movement, but it's not always possible to see that. If you can, it's an indication of creep, this very slow moving material. Or trees, if you've ever seen those growing at a weird angle like this, it's because as the trees try to grow straight up, then the slope is moving, so they have to bend to adjust so they can grow straight up and get more sunlight. Or maybe you see a fence that's been altered like this. All right. So real quick, and I'm running long, I didn't want to go too long. There isn't a ton of information here because those factors we talked about, naming conventions, that's kind of the key to this. But really fast, we want to say the two last things I want to cover is how do we kind of identify these and figure out, make them safe. And there's some triggering events, which are related to the factors that control whether a slope is stable or not. But real fast, you can go through these, like I said, at your own pace. But the big deal is water is a big driver for a lot of these failure events. So the way to stabilize slopes is to get the water out of the slope. And so mostly that's done with wells, whether that's a vertical or horizontal drains or wells to get rainwater out of the slope quickly. Even in Arizona, we've seen maybe these on some hill slopes by the roads. You're like, what the heck is that? All it is water hits the slope and moves down toward the roadway, intersects this flat area, and it can divert some of the water off the slope and down somewhere else, and so it doesn't absorb into the ground and then add weight and reduce internal friction and potentially cause problems. For places where we have really steep slopes and we're concerned about failure, we can just adjust the shape of the slope, cut and fill. We can do some benching like this if we want to, catch some of the material that might fall down even from our little steep slopes here. You see a lot of that, of course, when we build roadways. You can hold back some of the material. So if you have soils, thick soils, this works better in places on the east where This is probably strong enough to hold back some sediment for a while, but over time it'll fail. But in the short term, it's a decent solution. We can also do these kind of baskets. You might have seen those in places. The bonus to the walls that are made of this kind of chicken wire, which are called gabions, is that fluid can flow through here. So any water that strikes the wall can seep through, and that's useful. I don't know what else. You might have seen some little fencing like this to maintain some structural stability. Even spraying some of the rock with some concrete to give it some structural integrity. Sometimes you see that on roadways to just give some support to the rocks or even the sediment. And so what we do when we're looking at our lovely slopes here is we can make some general observations, because based on how gravity is working here, we can argue that there's a mass, a part of my slope that wants to move down slope, and then there's a part of my slope that it does not. It is actually hanging out, resisting motion. And so there has to be some type of balance here between these two. If this is greater than this, which means driving mass is greater than resisting mass, then we can have a problem. This is why in some areas where we build roads, we like to cut into the slope here and make our road nice and wide, and that's usually a bad idea because we're taking away some of this mass. So that's definitely not a good thing. The other thing besides just mass is we can look at forces involved. So we're taking on gravity, and we are looking at mass, we're looking at rock strength and things like that. And so we wouldn't want you to have to calculate formulas per se, but to understand that we're looking for this balance between resisting forces and driving forces. And this is related to the previous slide. They kind of intermix here, but it's still true that if we have a lot of resisting forces, they are big, it's a big number. And this is a small number that we would, if we did some math here with some numbers, we would get a number greater than 1 if the resisting forces are greater than the driving forces. So we can do some quick math if you're in the field, and then you can determine some stability and say we think this slope is fairly stable. If it's the other way around, where there's a lot of driving forces and not a lot of resisting forces, we would argue that the slope is unstable and could fail, in the near future. So there is some kind of back of the envelope calculations we can make in the field to try to figure out if a slope is stable or not, and then make some recommendations. Of course, another way is to map out areas that are stable or unstable for a variety of reasons. We could find old landslide events and say, hey, this has moved in the past, it could move in the future. We could evaluate weaker rocks, dipping beds, so all that kind of stuff. So just to, like for any hazard we come across, mapping and figuring out where the potential problems are is a way we could identify and then stabilize those things. And then the last thing that I'll let you cruise through yourself quickly, and I'll just blaze through, is there's triggering events, and certainly they're related to the factors that control slope stability, but any type of shock event could potentially trigger a mass wasting event. And usually we talk about how earthquakes could do that. But even explosions or things like that, even you think it's kind of weird, but on big roadways where trucks are booming by and making a lot of noise over time, those things could potentially shake the ground. And if there's steep slopes or weaknesses by, we can have events from that. But we certainly see that after big earthquakes because there's a lot of ground shaking. So that's a potential trigger. We saw that, sorry, I'm jumping around here, but we saw that in the Alaskan event, and big earthquake there. And just some images from that you can kind of look at. And, there's some other events that occurred like that where there was some earthquakes that induced a big rock fall, and we had these big avalanche areas that came down. But another triggering event that occurred. This was the previous picture that I showed you. You only saw this portion, but this is what it looked like before the avalanche came down. This is one of those big rock avalanches. So it's crazy the damage that they can do. And then, of course, we know water is a big factor, so a change in the amount of water. So a lot of events that we read in the news, it'll say, it rained for 30 days straight. Okay, so we get it. So that's why there was a big event there, because there was a change in what typically was happening. The ground got super saturated. So those events can cause mass wasting. And just an example of that, right? So this is one of those dipping bed stories, and there was a lot of rain. And so we caused a failure on the rock that slipped down into this lake, its reservoir, and caused some deaths from that. You can kind of read about that, and there's some images just so you can look at that. Volcanic eruptions, we already talked about. Those can produce lahars, so we know that because they potentially can shake the ground, that's a problem. They also can induce water because they melt snow and ice that might be on the top of our volcano. So we run into problems with that. And of course, just to give you an example, there was a pretty horrific event that happened where a volcano erupted, but really it wasn't a blast that was a problem, or ash or pyroclastic flows or anything like that. It melted a glacier that was up on the mountain, and the water mixed with all the loose material, and a huge mud flow just came racing down these very steep channels that are, valleys. But it ended up coming to this town here, just built in the open area, and a huge amount of material came in and washed into this area. And of course, there's a lot of people there, and there's, no fun for those people for sure. And so this was another indication that, wow, we should be aware that volcanoes can generate these big mass wasting events. All right, so I try to keep it short. 26, not bad. So that's all I got for you for this one, and then you can take a look at the articles and videos.